The directionality of heat transfer is another thing that's really important because, believe it or not, energy doesn't go necessarily in just one direction. But one thing we can say is that there are no examples of if you put a hot and a cold thing together, that the hot will get hotter and the cold will get colder, i.e., the heat does not go from the cold to the hot. Heat always transfers from the hot object to the cooler object, and that's an important kind of thing to consider. An exothermic reaction is when the heat goes from the system to the surroundings. So if you're having hydrogen and oxygen coming together to make water, a lot of energy is created by the system, and that energy has to go somewhere, so the energy goes to the surroundings, maybe to the other molecules or the container or whatever. So an exothermic reaction just means energy goes from the system to the surroundings. That little reaction right there, you can see there's all kinds of smoke and stuff being given off. That's a very exothermic reaction. Exothermic reactions are kind of exciting. They're explosions and stuff like that, but of course you have to control it to do anything meaningful. If you're measuring the temperature of the chemical reaction, almost inevitably, you're going to be measuring the temperature of the surroundings, because it's hard to measure like the hydrogen and the oxygen molecules, but it's easy if they're in, say, air, or if it's in water, it's easy to measure the surroundings. So if you're measuring the surroundings, which you almost always are, your temperature is going to go up because the system is giving its energy to the surroundings. The surrounding temperature is going to increase. So if you talk about an exothermic reaction, that's the energy going from the system to the surroundings, and your temperature, which measures again the surroundings almost all the time, will be increasing. You'll actually see the temperature go up, and that's what we'll see. So if you see a reaction where the temperature is increasing, that means it's exothermic. Energy is given off. You might also feel the energy. If you feel the system or the container that was holding the reaction, you might feel it go up too, but the temperature, of course, would be a quantitative way to do that. But not all reactions are exothermic. There's also reactions that are endothermic. And in an endothermic reaction, the energy goes from the surrounding to the system. And let's use an example which is hopefully meaningful. If you leave your ice out on the table for a while, it starts to melt. Now, ice is really cold, all right? Ice is absorbing the energy from the surroundings and transferring it to the system, essentially. This is an endothermic reaction, all right? It actually feels like it's colder all of a sudden, but you know that the ice is melting. You can see it, all right? So the ice, the system, is pulling energy from the surroundings, and this is what an endothermic reaction is. If you are measuring the surroundings again, which is what you almost always do, the temperature of these is going to decrease. It's going to feel cold, all right? So the thermometer is a valuable tool for the chemist. If the thermometer goes up, it means exothermic. If the thermometer temperature goes down, endothermic. And you can then talk about surroundings and systems and what happens. Here's an example. A chemical reaction feels warm upon completion, and no outside source of heat was added. And can you make the call as to if this reaction is exothermic, endothermic, neither endothermic or exothermic, or you need more information? Well, again, the heat is the big thing. And if it feels warm, that's the same as putting the thermometer in and watching the temperature go up. And if it goes up, that means the system gave energy to the surroundings. That means that there's going to be an energy released by the system, and that's the exothermic reaction. So again, if you feel a chemical container getting warmer, exothermic reaction, and you would see if you measured it, then the thermometer temperature would go up, you'd be good to go. If the reaction felt cold, it would be endothermic. And I would argue that all reactions are endothermic or exothermic. You can't have it exactly at the 0 point. I don't think you'd have any transformations if that was possible. And again, most of the time, just feeling it is enough to answer this question. Enthalpy is the name given when heat is transferred at constant pressure, and enthalpy gets the symbol delta H. Now, heat transferred, Q, which is heat transferred at constant pressure is given the symbol Q sub P. So we're going to start talking a lot about enthalpy, and enthalpy is like a special form of heat transfer. You can have heat transferred under non-standard pressures, all right? It would be like pressure that oscillates or something like that. So Q sub P is not a universal thing, but most of the time at room temperature and room pressure, when you're measuring heat, it is measured at constant pressure. So delta H is kind of a real important tool that chemists use to describe if a reaction is exothermic or endothermic. And how they use the enthalpy values is looking at the magnitude. If delta H is greater than 0, or if delta H is less than 0, that's going to tell us something. And if delta H is greater than 0, we're going to call those endothermic reactions. And if delta H is less than 0, those are going to be exothermic reactions. So exothermic means that energy is being released by the system. Your delta H is negative. On the other hand, endothermic, the system is absorbing the energy from their surroundings. Delta H is going to be positive. I like to think of a positive delta H as energy going into the system, into the middle part. On the other hand, if you have a negative delta H in exothermic, energy is released from the inside to the outside. There's going to be a whole bunch of different delta H's. Delta H vap, delta H reaction, delta HF. But all of them, the sign of delta H will tell you if there's endothermic or exothermic, i.e. would you need to add energy, i.e. endothermic, or will you get energy out, which is exothermic. And the person down here in the picture, some kind of musician, they called themselves Enthalpy. I thought that was kind of cool. The delta H is backwards, but anyway, what are you going to do? Art and science. Anyway, so going back to the first law of thermodynamics, delta E equals Q plus W, heat plus work. And most of the time, heat is transferred at constant pressure. So you can substitute in delta E equals delta H if it's constant pressure plus work. And again, because almost always the work is like 0 in chemistry, most of the time enthalpy delta H will equal the total energy of the system. So we're going to do a lot of stuff here coming up about enthalpy, all right? And chemists use that to tell how the overall energy of the system is. Just remember, delta H negative exothermic, delta H positive endothermic, will be good to go. But it does assume A, that you're at constant pressure, which is most of the time, but not all the time. And B, it assumes there's no work on the system. And in chemistry, that's a pretty fair bet, although there are exceptions. In physics, you wouldn't dare do that. There's a lot of work functions. The quantity delta H, it's the enthalpy of the reaction. So this is the first type of delta H we're seeing, delta H RXN. It's the heat of reaction, and it's measured in kilojoules per mole. And the pictures here show a balloon with hydrogen inside and a little flame there to get the party started, if you will. And the hydrogen reacts with oxygen on the outside to make water, and there's a lot of energy released. So this little diagram right here shows how chemists think about this. Enthalpy is along the y-axis. And notice here how the reactants are at the top, the hydrogen and the oxygen, and water, the product, is at the bottom. So delta H here is going to be a negative number. The delta H is going down. That means it's an exothermic reaction. So notice that in this case, the energy went from the system to the surroundings, and that extra energy was released as energy to the surroundings. This is an exothermic reaction. If your products are at a lower energy than the reactants, that's going to be exothermic. If this was an endothermic reaction, then your reactants would be at a lower energy than your products. I'll just put some arbitrary line right there. And this is another way that you can use to think about what energy means. Delta H for a reaction in the forward direction is equal in size but opposite in sign to delta H in the reverse reaction. So let's talk about what that means. Here on the lower left is another example. This is methane CH4 plus 2 oxygen going to CO2 and water. And let's focus first of all on the down arrow. And that says that the CH4 and 2 O2s are the reactants, and the CO2 and 2H2O are the products. And the delta H, the enthalpy of that reaction, negative 890 kilojoules. So an exothermic reaction. And this is burning essentially natural gas. This is what happens. A lot of energy is released. However, if you were curious about the energy change going from carbon dioxide and 2 waters up to methane and 2 oxygens, notice the arrow here on this side is reversed. It's going up instead of down. And notice the delta H2 relative to delta H1. They're both 890 kilojoules, but the first reaction was exothermic, negative delta H. The second reaction is positive endothermic delta H. So again, what that first sentence up there said is that if you reverse a reaction, you basically have the same magnitude but opposite sign. So we went from negative 890 kilojoules to a positive 890 kilojoules. This is interesting in thermodynamics. One direction will be exothermic, one direction will be endothermic, and the magnitude is the same, you just change the sign. The delta H for reaction does depend on the state of products and the state of the reactants. So notice that H2O liquid is one of the products if you go from the CH4 down to the CO2 and water. If we change that to CO2 and H2O gas, we would have to recalculate our delta H values. Everything is very state dependent. It takes more energy sometimes to get to a gas versus a liquid versus a solid, etc., etc. We can't know the exact enthalpy of reactants and products, but you can measure these delta H values through calorimetry. And calorimetry is the study of heat flow. And it uses something called a bomb calorimeter, which has a really cool name. It's not really a bomb, okay? But anyway, you put the little sample inside the bomb calorimeter, and there's a whole bunch of water around, and you basically ignite it, all right? And you stir it up and stuff, and you measure the delta H, the heat change as the reaction proceeds, and you can use this and stuff in order to find these delta H values. At the end of this lecture series, this section, I will show you an example of how you could use a bomb calorimeter. Pretty cool. But anyway, calorimetry is just basically the study of these heat energies and how they work.
Heat, or thermal energy, is associated with the motions of atoms and molecules in a substance. The more rapid these atomic scale motions, the greater a substance's thermal energy and the hotter it is. When we plunge a hot metal bar into cool water, thermal energy from the bar transfers to the water. While the atoms and molecules of the bar slow down, those of the water speed up. The transfer of energy can be measured as a rise in water temperature.
Molecules of a hot substance move more rapidly than those of the same substance with a lower temperature. If the two samples come in contact, a transfer of molecular momentum occurs from the rapidly moving molecules to the slower ones. In this way, thermal energy transfers from the hotter sample to the cooler one. When the two samples have similar rates of molecular motion, they have reached thermal equilibrium and have the same temperature.
No examples have been observed of when hot and cold comes together and the hot gets hotter and the cold gets colder. That just doesn't happen. If it ever does happen, we're going to have to rewrite calorimetry and thermodynamics big time. But in the meantime, anyway, if you put hot and cold together, the hot transfers its heat to the cold, and you end up with two things at the same temperature, which in this little animation there says warm, all right? And that's that's how all the calorimetry works. Hot goes to cold. The hot metal in the cold water, you could see the cold water's temperature increase. The heat was being transferred from the hot metal to the cold water until they became warm. And it happens until thermal equilibrium is established. And thermal equilibrium just means there's no more heat change. And that depends, of course, on the temperature of your surroundings and all that kind of stuff. But there will be some place where hot and cold come together and they reach a warm temperature, thermal equilibrium. This is the kinetic molecular theory again. We talked about this in chapter 1, and it kind of comes back and forth in chemistry. This is the idea of how hot and cold works. Hot has lots of energy, lots of motion. It transfers the motion to the cold things until everything is kind of in between. Oh, poor Robin. Robin says, "Close the window. You're letting the cold in." And then Batman slaps him, which is kind of violent. I apologize. But Batman goes, "Thermodynamics too. The heat goes out." All right. Really, calorimetry, thermodynamics, it's about heat transfer. All right. It's not about cold. If you're opening the window, all right, the heat is basically leaving. It's not the cold coming in. It's the heat leaving. Heat is the energy. All right. Cold is just sitting there and stuff like that. So anyway, it's a dumb diagram and stuff, but hopefully it brought a smile to your face.